Stanford University.
Hello? Okay, it's after 12, so I want to get started. So today, lecture 8, we're going to talk about deep learning software. This is a super exciting topic because it changes a lot every year. That also means it's a lot of work to give this lecture because it changes a lot every year. But as usual, a couple administrative notes before we dive into the material. So as a reminder, the project proposals for your course projects were due on Tuesday. So hopefully you all turned that in, and hopefully you all have a somewhat good idea of what kind of projects you want to work on for the class. So we're in the process of assigning TAs to projects based on what the project area is and the expertise of the TAs. So we'll have some more information about that in the next couple of days, I think. We're also in the process of grading assignment 1, so stay tuned, and we'll get those grades back to you as soon as we can. Another reminder is that assignment 2 has been out for a while. That's going to be due next week, a week from today, Thursday. And again, when working on assignment 2, remember to stop your Google Cloud instances when you're not working to try to preserve your credits. And again, another bit of confusion I just wanted to reemphasize is that for assignment 2, you really only need to use GPU instances for the last notebook. For all the first several notebooks, it's just in Python and NumPy, so you don't need any GPUs for those questions. So again, conserve your credits, only use GPUs when you need them. And the final reminder is that the midterm is coming up. It's kind of hard to believe we're there already, but the midterm will be in class on Tuesday, 5/9. So the midterm will be more theoretical. It'll be sort of pen and paper, working through different kinds of slightly more theoretical questions to check your understanding of the material we've covered so far. And I think we'll probably post at least a short sort of sample of the types of questions to expect. Question? Oh, yeah, question is whether it's open book. So we're going to say closed note, closed book. So just, yeah. So that's what we've done in the past, is just closed note, closed book, relatively just like want to check that you understand the intuition behind most of the stuff we presented. So a quick recap, as a reminder of what we were talking about last time. Last time we talked about fancier optimization algorithms for deep learning models, including SGD momentum, Nesterov, RMS prop, and Atom. And we saw that these relatively small tweaks on top of vanilla SGD are relatively easy to implement, but can make your networks converge a bit faster. We also talked about regularization, especially dropout. So remember, dropout, you're kind of randomly setting parts of the network to 0 during the forward pass, and then you kind of marginalize out over that noise in the back at test time. And we saw that this was kind of a general pattern across many different types of regularization in deep learning, where you might add some kind of noise during training, but then marginalize out that noise at test time, so it's not stochastic at test time. We also talked about transfer learning, where you can maybe download big networks that were pre-trained on some data set, and then fine-tune them for your own problem. And this is one way that you can attack a lot of different problems in deep learning, even if you don't have a huge data set of your own. So today we're going to shift gears a little bit and talk about some of the nuts and bolts about like writing software and how the hardware works, and a little bit diving into a lot of details about what the software looks like that you actually use to train these things in practice. So we'll talk a little bit about CPUs and GPUs, and then we'll talk about several of the major deep learning frameworks that are out there in use these days. So first, we've sort of mentioned this offhand a bunch of different times, that there's like computers have CPUs, computers have GPUs, deep learning uses GPUs, but we weren't really too explicit up to this point about what exactly these things are and why one might be better than another for different tasks. So who's built a computer before? Just kind of show of hands. So maybe about a third of you, half of you, somewhere around that ballpark. So this is a shot of my computer at home that I built, and you can see that like there's a lot of stuff going on inside the computer. Hopefully you know what most of these parts are. And the CPU is the central processing unit. That's this little chip hidden under this cooling fan right here near the top of the case. And the CPU is actually a relatively small piece, like it's a relatively small thing inside the case. It's not taking up a lot of space. And the GPUs are these two big monster things that are taking up a gigantic amount of space in the case. They have their own cooling. They're taking a lot of power. They're quite large. So just in terms of like how much power they're using, in terms of how big they are, the GPUs are kind of physically imposing and taking up a lot of space in the case. So the question is like, what are these things, and why are they so important for deep learning? Well, the GPU is called a graphics card or graphics processing unit. And these were really developed originally for rendering computer graphics, and especially around games and that sort of thing. So another show of hands, who's plays video games at home sometimes from time to time on their computer? Yeah, so again, like maybe about half, good fraction. So for those of you who've played video games before and who've built your own computers, you probably have your own opinions on this debate. So this is one of those like big debates in computer science. Is like there's like Intel versus AMD and NVIDIA versus AMD for graphics cards. It's maybe up there with Vim versus Emacs for text editor. And pretty much any gamer has their own opinions on which of these two sides they prefer for their own cards. And in deep learning, we kind of have mostly picked one side of this fight, and that's NVIDIA. So if you guys have AMD cards, you might be in a little bit more trouble if you want to use those for deep learning. And really, NVIDIA has been pushing a lot for deep learning in the last several years. It's been kind of a large focus of some of their strategy. And they put a lot of effort into engineering sort of good solutions to make their hardware better suited for deep learning. So most people in deep learning, when we talk about GPUs, we're pretty much exclusively talking about NVIDIA GPUs. Maybe in the future, this will change a little bit, and there might be new players coming up. But at least for now, NVIDIA is pretty dominant. So to give you an idea of like what is the difference between a CPU and a GPU, I've kind of made a little spreadsheet here. On the top, we have two of the kind of top-end Intel consumer CPUs. And on the bottom, we have two of NVIDIA's sort of current top-end consumer GPUs. And there's a couple general trends to notice here. Both GPUs and CPUs are kind of a general purpose computing machine where they can execute programs and do sort of arbitrary instructions, but they're qualitatively pretty different. So CPUs tend to have just a few cores. For consumer desktop CPUs these days, they might have something like 4 or 6 or maybe up to 10 cores. With hyperthreading technology, that means they can run, the hardware can physically run like maybe 8 or up to 20 threads concurrently. So the CPU can maybe do 20 things in parallel at once, which is not a gigantic number. But those threads for a CPU are pretty powerful. They can actually do a lot of things. They're very fast. Every CPU instruction can actually do quite a lot of stuff, and they can all work pretty independently. For GPUs, it's a little bit different. So for GPUs, we see that these sort of common top-end consumer GPUs have thousands of cores. So the NVIDIA Titan XP, which is the current top-of-the-line consumer GPU, has 3,840 cores. So that's a crazy number. That's like way more than the 10 cores that you'll get for a similarly priced CPU. The downside of a GPU is that each of those cores, one, it runs at a much lower clock speed, and two, they really can't do quite as much. You can't really compare CPU cores and GPU cores apples to apples. The GPU cores can't really operate very independently. They all kind of need to work together and sort of parallelize one task across many cores rather than each core totally doing its own thing. So you can't really compare these numbers directly, but it should give you this sense that due to the large number of cores, GPUs are really good for parallel things where you need to do a lot of things all at the same time, but those things are all pretty much the same flavor. Another thing to point out between CPUs and GPUs is this idea of memory, right? So CPUs have some cache on the CPU, but that's relatively small. And the majority of the memory for your CPU is pulling from your system memory, the RAM, which will maybe be like 8, 12, 16, 32 gigabytes of RAM on a typical consumer desktop these days. Whereas GPUs actually have their own RAM built into the chip. There's a pretty large bottleneck communicating between the RAM in your system and the GPU. So that GPUs typically have their own relatively large block of memory within the card itself. And for the Titan XP, which again is maybe the current top-of-the-line consumer card, this thing has 12 gigabytes of memory local to the GPU. GPUs also have their own caching system where there's sort of multiple hierarchies of caching between the 12 gigabytes of GPU memory and the actual GPU cores. And that's somewhat similar to the caching hierarchy that you might see in a CPU. So CPUs are kind of good for general purpose processing. They can do a lot of different things. And GPUs are maybe more specialized for these highly parallelizable algorithms. So the prototypical algorithm of something that works really, really well and is like perfectly suited to a GPU is matrix multiplication. So remember in matrix multiplication, on the left, we've got like a matrix composed of a bunch of rows. We multiply that on the right by another matrix composed of a bunch of columns. And then this produces a final matrix where each element in the output matrix is a dot product between one of the rows and one of the columns of the two input matrices. And these dot products are all independent. Like you could imagine sort of for this output matrix, you could split it up completely and have each of those different elements of the output matrix all being computed in parallel. And they all sort of are running the same computation, which is taking a dot product of these two vectors. But exactly where they're reading that data from is from different places in the two input matrices. So you could imagine that for a GPU, you can just like blast this out and have all of these elements of the output matrix all computed in parallel. And that could make this thing actually compute super, super fast on GPU. So that's kind of the prototypical type of problem that where a GPU is really well suited, where a CPU might have to go in and step through sequentially and compute each of these elements one by one. That picture is a little bit of a caricature because CPUs these days have multiple cores. They can do vectorized instructions as well. But still, for these like massively parallel problems, GPUs tend to have much better throughput, especially when these matrices get really, really big. And by the way, convolution is kind of the same kind of story, where in convolution, we have this input tensor, we have this weight tensor, and then every point in the output tensor after convolution is again some inner product between some part of the weights and some part of the input. And you can imagine that a GPU could really parallelize this computation, split it all up across the many cores, and compute it very quickly. So that's the kind of the general flavor of the types of problems where GPUs give you a huge speed advantage over CPUs. So you can actually write programs that run directly on GPUs. So NVIDIA has this CUDA abstraction, which lets you write code that kind of looks like C, but executes directly on the GPUs. But writing CUDA code is really, really tricky. It's actually really tough to write CUDA code that's performant and actually squeezes all the juice out of these GPUs. You have to be very careful managing the memory hierarchy and making sure you don't have cache misses and branch miss predictions and all that sort of stuff. So it's actually really, really hard to write performant CUDA code on your own. So as a result, NVIDIA has released a lot of libraries that implement common computational primitives that are very, 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 very highly optimized for GPUs. So for example, NVIDIA has a cuBLAST library that implements different kinds of matrix multiplications and different matrix operations that are super optimized, run really well on GPU, get very close to sort of theoretical peak hardware utilization. Similarly, they have a cuDNN library, which implements things like convolution, forward and backward passes, batch normalization, recurrent networks, all these kinds of computational primitives that we need in deep learning. NVIDIA has gone in there and released their own binaries that compute these primitives very efficiently on NVIDIA hardware. So in practice, you tend not to end up writing your own CUDA code for deep learning. You typically are just mostly calling into existing code that other people have written, much of which is this stuff which has been heavily optimized by NVIDIA already. There's another sort of language called OpenCL, which is a bit more general, runs on more than just NVIDIA GPUs, can run on AMD hardware, can run on CPUs. But OpenCL nobody's really spent a really large amount of effort and energy trying to get optimized deep learning primitives for OpenCL. So that tends to be a lot less performant than the super optimized versions in CUDA. So maybe in the future, we might see a bit of a more open standard, and we might see this across many different more types of platforms. But at least for now, NVIDIA is kind of the main game in town for deep learning. So you can check, there's a lot of different resources for learning about how you can do GPU programming yourself. It's kind of fun. It's sort of a different paradigm of writing code because it's this massively parallel architecture. But that's a bit beyond the scope of this course. And again, you don't really need to write your own CUDA code much in practice for deep learning. And in fact, I've never written my own CUDA code for any research project. But it is kind of useful to know like how it works and what are the basic ideas, even if you're not writing it yourself. So if you want to look at kind of CPU, GPU performance in practice, I did some benchmarks last summer comparing a relatively, or like a decent Intel CPU against a bunch of different GPUs that were sort of near top of the line at that time. And these were my own benchmarks that you can find more details on GitHub. But my findings were that like for things like VGG, 16 and 19, ResNets, various ResNets, then you typically see like something like a 65 to 75 times speed up when running the exact same computation on a top-of-the-line GPU, in this case a Pascal Titan X, versus a top-of-the-line, well, not quite top-of-the-line CPU, which in this case was an Intel E5 processor. Although I'd like to make one sort of caveat here is that you always need to be super careful whenever you're reading any kind of benchmarks about deep learning, because it's super easy to be unfair between different things. And you kind of need to know a lot of the details about what exactly is being benchmarked in order to know whether or not the comparison is fair. So in this case, I'll come right out and tell you that probably this comparison is a little bit unfair to CPU because I didn't spend a lot of effort trying to squeeze the maximal performance out of CPUs. I probably could have tuned the BLAST libraries better for the CPU performance, and I probably could have gotten these numbers a bit better. This was sort of out-of-the-box performance between like just installing Torch, running it on a CPU, just installing Torch, running it on a GPU. So this is kind of out-of-the-box performance, but it's not really like peak possible theoretical throughput on the CPU. But that being said, I think there are still pretty substantial speedups to be had here. Another kind of interesting outcome from this benchmarking was comparing these optimized cuDNN libraries from NVIDIA for convolution and whatnot versus sort of more naive CUDA that had been handwritten out in the open source community. And you can see that if you compare the same networks on the same hardware with the same deep learning framework, and the only difference is swapping out these cuDNN versus sort of handwritten, less optimized CUDA, you can see something like nearly a 3x speedup across the board when you switch from this relatively simple CUDA to these like super optimized cuDNN implementations. So in general, whenever you're writing code on GPU, you should probably almost always like just make sure you're using cuDNN because you're leaving probably a 3x performance boost on the table if you're not calling into cuDNN for your stuff. So another problem that comes up in practice when you're training these things is that your model is maybe sitting on the GPU. The weights of the model are in that 12 gigabytes of local storage on the GPU, but your big data set is sitting over on the right on a hard drive or an SSD or something like that. So if you're not careful, you can actually bottleneck your training by just trying to read the data off the disk. It's because the GPU is super fast. It can compute forward and backward quite fast. But if you're reading sequentially off a spinning disk, you can actually bottleneck your training and that can be really bad and slow you down. So some solutions here are that if your data set's really small, sometimes you might just read the whole data set into RAM. Or even if your data set isn't so small, but you have a giant server with a ton of RAM, you might do that anyway. You can also make sure you're using an SSD instead of a hard drive. That can help a lot with read throughput. Another common strategy is to use multiple threads on the CPU that are prefetching data off RAM or off disk, buffering it in memory in RAM, so that then you can continue feeding that buffered data down to the GPU with good performance. This is a little bit painful to set up, but again, these GPUs are so fast that if you're not really careful with trying to feed them data as quickly as possible, just reading the data can sometimes bottleneck the whole training process. So that's something to be aware of. So that's kind of the brief introduction to sort of GPU, CPU hardware in practice when it comes to deep learning. And then I wanted to switch gears a little bit and talk about the software side of things, the various deep learning frameworks that people are using in practice. But I guess before I move on, is there any sort of questions about CPU, GPU? Yeah, question? Yeah, so the question is what can you do mechanically when you're coding to avoid these problems? Probably the biggest thing you can do in software is set up sort of prefetching on the CPU. You couldn't, sort of a naive thing would be you have this sequential process where you first read data off disk, wait for the mini batch to be read, then feed the mini batch to the GPU, then go forward and backward on the GPU, then read another mini batch and sort of do this all in sequence. And if you actually have multiple, instead you might have CPU threads running in the background that are fetching data off the disk, such that you can sort of interleave all of these things. Like the GPU is computing, the CPU background threads are feeding data off disk, and your main thread is kind of waiting for these things to just doing a bit of synchronization between these things, so they're all happening in parallel. And thankfully, if you're using some of these deep learning frameworks that we're about to talk about, then some of this work has already been done for you because it's a little bit painful. So the landscape of deep learning frameworks is super fast moving. So last year when I gave this lecture, I talked mostly about Caffe, Torch, Theano, and TensorFlow. And when I last gave this talk again, more than a year ago, TensorFlow was relatively new. It had not seen super widespread adoption yet at that time. But now I think in the last year, TensorFlow has gotten much more popular. It's probably the main framework of choice for many people. So that's a big change. We've also seen a ton of new frameworks sort of popping up like mushrooms in the last year. So in particular, Caffe2 and PyTorch are new frameworks from Facebook that I think are pretty interesting. There's also a ton of other frameworks. Paddle, like Baidu has Paddle. Microsoft has CNTK. Amazon is mostly using MXNet. And there's a ton of other frameworks as well that I'm less familiar with and really don't have time to get into. But one interesting thing to point out from this picture is that kind of the first generation of deep learning frameworks that really saw wide adoption were built in academia. So Caffe was from Berkeley. Torch was developed originally at NYU and also in collaboration with Facebook. And Theano was mostly built at University of Montreal. But these kind of next generation deep learning frameworks all originated in industry. So Caffe2 is from Facebook, PyTorch is from Facebook, TensorFlow is from Google. So that's kind of an interesting shift that we've seen in the landscape over the last couple of years, is that these ideas have really moved a lot from academia into industry. And now industry is kind of giving us these big, powerful, nice frameworks to work with. So today I wanted to mostly talk about PyTorch and TensorFlow, because I personally think that those are probably the ones you should be focusing on for a lot of research type problems these days. I'll also talk a bit about Caffe and Caffe2, but probably a little bit less emphasis on those. And before we move any farther, I thought I should make my own biases a little bit more explicit. So I've worked with Torch mostly for the last several years, and I've used it quite a lot. I like it a lot. And then in the last year, I've mostly switched to PyTorch as my main research framework. So I have a little bit less experience with some of these others, especially TensorFlow, but I'll still try to do my best to give you a fair picture and a decent overview of these things. So, remember that in the last several lectures, we've hammered this idea of computational graphs in sort of over and over. That whenever we're doing deep learning, you want to think about building some computational graph that computes whatever function that you want to compute. So in the case of a linear classifier, you'll combine your data x and your weights w with a matrix multiply. You'll do some kind of hinge loss to maybe compute your loss. You have some regularization term. And you imagine stitching together all these different operations into some graph structure. Remember that these graph structures can get pretty complex. In the case of a big neural net, now there's many different layers, many different activations, many different weights spread all around in a pretty complex graph. And as you move to things like neural Turing machines, then you can get these really crazy computational graphs that you can't even really draw because they're so big and messy. So the point of deep learning frameworks is really, there's really kind of three main reasons why you might want to use one of these deep learning frameworks rather than just writing your own code. So the first would be that these frameworks enable you to easily build and work with these big, hairy computational graphs without kind of worrying about a lot of those bookkeeping details yourself. Another major idea is that whenever we're working in deep learning, we always need to compute gradients. We're always computing some loss. We're always computing gradient of our weights with respect to the loss. And we'd like to make this automatically computing gradients. You don't want to have to write that code yourself. You want the framework to handle all these backpropagation details for you, so you can just think about writing down the forward pass of your network and have the backward pass sort of come out for free without any additional work. And finally, you want all this stuff to run efficiently on GPUs, so you don't have to worry too much about these low-level hardware details about cuBLAS and cuDNN and CUDA and moving data between the CPU and GPU memory. You kind of want all those messy details to be taken care of for you. So those are kind of some of the major reasons why you might choose to use frameworks rather than writing your own stuff from scratch. So as kind of a concrete example of a computational graph, look, we can maybe write down this super simple thing where we have three inputs x, y, and z. We're going to combine x and y to produce A. Then we're going to combine A and Z to produce B. And then finally, we're going to do some maybe summing out operation on B to give some scalar final result C. So you've probably written enough NumPy code at this point to realize that it's super easy to write down, to implement this computational graph, or rather to implement this bit of computation in NumPy. Right? And you can just kind of write down in NumPy that you want to generate some random data, you want to multiply two things, you want to add two things, you want to sum out a couple things, and it's really easy to do this in NumPy. But then the question is, suppose that we want to compute the gradient of C with respect to x, y, and z. So if you're working in NumPy, you kind of need to write out this backward pass yourself. And you've gotten a lot of practice with this on the homeworks. but it can be kind of a pain and a little bit annoying and messy once you get to really big, complicated things. The other problem with NumPy is that it doesn't run on the GPU. So NumPy is definitely CPU only, and you're never going to be able to experience or take advantage of these GPU accelerated speedups if you're just stuck working in NumPy. And again, it's a pain to have to compute your own gradients in all these situations. So kind of the goal of most deep learning frameworks these days is to let you write code in the forward pass that looks very similar to NumPy, but lets you run it on the GPU and lets you automatically compute gradients. And that's kind of the big picture goal of most of these frameworks. So if you imagine if we look at an example in TensorFlow of the exact same computational graph, we now see that in this forward pass, you write this code that ends up looking very, very similar to the NumPy forward pass, where you're kind of doing these multiplication and these addition operations. But now TensorFlow has this magic line that just computes all the gradients for you. So now you don't have to go in and write your own backward pass, and that's much more convenient. The other nice thing about TensorFlow is you can really just, with one line, you can switch all this computation between CPU and GPU. So here, if you just add this with statement before you're doing this forward pass, you just can explicitly tell the framework, hey, I want to run this code on the CPU. But now if you just change that with statement a little bit with just like a one character change in this case, changing that C to a G, now the code runs on GPU. And now in this little code snippet, we've solved these two problems. We're running our code on the GPU, and we're having the framework compute all the gradients for us. So that's really nice. And PyTorch kind of looks almost exactly the same. So again, in PyTorch, you kind of write down you define some variables. You have some forward pass, and the forward pass, again, looks very similar to, like, in this case, identical to the NumPy code. And then, again, you can just use PyTorch to compute gradients, all your gradients with just one line. And now in PyTorch, again, it's really easy to switch to GPU. You just need to cast all your stuff to the CUDA data type before you run your computation. And now everything runs transparently on the GPU for you. So if you kind of just look at these three these three snippets of code side by side, the NumPy, the TensorFlow, and the PyTorch, you see that like the TensorFlow and the PyTorch code in the forward pass looks almost exactly like NumPy, which is great because NumPy has a beautiful API. It's really easy to work with. But we can compute gradients automatically, and we can run the GPU automatically. So after that kind of introduction, I wanted to dive in and talk in a little bit more detail about what's going on inside this TensorFlow example. So as a running example throughout the rest of the lecture, I'm going to use training a 2-layer fully connected ReLU network on random data as kind of a running example throughout the rest of the examples here. And we're going to train this thing with an L2 Euclidean loss on random data. So this is kind of a silly network. It's not really doing anything useful, but it does give you the sense. It's relatively small, self-contained. The code fits on the slide without being too small, and it lets you demonstrate kind of a lot of the useful ideas inside these frameworks. So here on the right, and then another note, I'm kind of assuming that NumPy and TensorFlow have already been imported in all these code snippets. So in TensorFlow, you typically divide your computation into two major stages. First, we're going to write some code that defines our computational graph, and that's this red code up in the top half. And then after you define your graph, you're going to run the graph over and over again and actually feed data into the graph to perform whatever computation you wanted to perform. So this is kind of the big common pattern in TensorFlow. You'll first have a bunch of code that builds the graph, and then you'll go and run the graph and reuse it many, many times. So if you kind of dive into the code of building the graph in this case, up at the top, you see that we're defining this x, y, w1, and w2, and we're creating these tf.placeholder objects. So these are going to be input nodes to the graph. These are going to be sort of entry points to the graph, where when we run the graph, we're going to feed in data and put them into these input slots in our computational graph. So this is not actually like allocating any memory right now. We're just sort of setting up these input slots to the graph. Then we're going to use those input slots, which are now kind of like these symbolic variables. And we're going to perform different TensorFlow operations on these symbolic variables in order to set up what computation we want to run on those variables. So in this case, we're doing a matrix multiplication between x and w1. We're doing some tf.maximum to do a ReLU nonlinearity, and then we're doing another matrix multiplication to compute our output predictions. And then we're, again, using sort of basic tensor operations to compute our Euclidean distance, our L2 loss between our prediction and the target y. Another thing to point out here is that these lines of code are not actually computing anything. There's no data in the system right now. We're just building up this computational graph data structure, telling TensorFlow which operations we want to eventually run once we put in real data. So this is just building the graph. This is not actually doing anything. Then we have this magical line where after we've computed our loss with these symbolic operations, then we can just ask TensorFlow to compute all these the gradient of the loss with respect to W1 and W2 in this one magical, beautiful line. And this avoids you writing all your own backprop code that you had to do in the assignments. But again, there's no actual computation happening here. This is just sort of adding extra operations to the computational graph, where now the computational graph has these additional operations which will end up computing these gradients for you. So now at this point, we've computed our computational graph. We have this big graph and this graph data structure in memory that knows like what operations we want to perform to compute the loss and gradients. And now we enter a TensorFlow session to actually run this graph and feed it with data. So then once we've entered the session, then we actually need to construct some concrete values that will be fed to the graph. So TensorFlow just expects to receive data from NumPy arrays in most cases. So here we're just creating concrete actual values for x, y, w1, and w2 using NumPy, and then storing these in some dictionary. And now here is where we're actually running the graph. So you can see that we're calling session.run to actually execute some part of the graph. The first argument, loss, tells us which part of the graph do we actually want as output. So we actually want the graph. In this case, we need to tell it that we actually want to compute loss and grad1 and grad w2. And we need to pass in with this feeddict parameter the actual concrete values that will be fed to the graph. And then after in this one line, it's going and running the graph and then computing those values for loss, grad1, grad w2, and then returning the actual concrete values for those in NumPy arrays again. So now after you unpack this output in the second line, you get NumPy arrays, or you get NumPy arrays with the loss, the gradient, and with the loss and the gradients. So then you can go and do whatever you want with these values. So then it's only a pretty, so this has only run sort of one forward and backward pass through our graph, and it only takes a couple extra lines if we actually want to train the network. So here now we're running the graph many times in a loop. So we're doing a for loop, and in each iteration of the loop, we're calling session.run, asking it to compute the loss and the gradients. And now we're doing a manual gradient descent step using those computed gradients to now update our current values of the weights. So if you actually run this code and plot the losses, then you'll see that the loss goes down and the network is training, and this is working pretty well. So this is kind of like a super bare bones example of training a fully connected network in TensorFlow. But there's a problem here. So here, remember that on the forward pass, every time we execute this graph, we're actually feeding in the weights. We have the weights as NumPy arrays, and we're explicitly feeding them into the graph. And now when the graph finishes executing, it's going to give us these gradients. And remember, the gradients are the same size as the weights. So this means that every time we're running the graph here, we're copying the weights from NumPy arrays into TensorFlow, then getting the gradients, and then copying the gradients from TensorFlow back out to NumPy arrays. So if you're just running on CPU, this is maybe not a huge deal. But remember, we talked about CPU, GPU bottleneck and how it's very expensive actually to copy data between CPU memory and GPU memory. So if your network was very large and your weights and gradients were very big, then doing something like this would be super expensive and super slow because we'd be copying all kinds of data back and forth between the CPU and the GPU at every time step. So that's bad. We don't want to do that. We need to fix that. So obviously, TensorFlow has some solution to this. And the idea is that now we want our weights, W1 and W2, rather than being placeholders where we expect to feed them into the network on every forward pass, instead we define them as variables. So a variable is something that is a value that lives inside the computational graph, and it's going to persist inside the computational graph across different times when we run the same graph. So now, instead of declaring these W1 and W2 as placeholders, instead we just construct them as variables. But now, since they live inside the graph, we also need to tell TensorFlow how they should be initialized, right? Because in the previous case, we were feeding in their values from outside the graph, so we initialized them in NumPy. But now, because these things live inside the graph, TensorFlow is responsible for initializing them. So we need to pass in a tf.randomNormal operation, which again is not actually initializing them when we run this line. This is just telling TensorFlow how we want them to be initialized. So it's a little bit of confusing misdirection going on here. And now remember, in the previous example, we were actually updating the weights outside of the computational graph. In the previous example, we were computing the gradients and then using them to update the weights as NumPy arrays, and then feeding in the updated weights at the next time step. But now, because we want these weights to live inside the graph, this operation of updating the weights needs to also be an operation inside the computational graph. So now we use this assign function, which mutates these variables inside the computational graph. And now the mutated value will persist across multiple runs of the same graph. So now when we run this graph and when we train the network, now we need to run the graph once with a bit of special incantation to tell TensorFlow to set up these variables that are going to live inside the graph. And then once we've done that initialization, now we can run the graph over and over again. And here we're only feeding in the data and labels x and y, and the weights are living inside the graph. And here we've asked TensorFlow to compute the loss for us. And then you might think that this would train the network. But there's actually a bug here. So if you actually run this code and you plot the loss, it doesn't train. So that's bad. It's confusing. Like, what's going on? We wrote this assign code. We ran the thing. Like, we computed the loss and the gradients. And our loss is flat. What's going on? Any ideas? Yeah, so one hypothesis was that maybe we're accidentally reinitializing the w's every time we call the graph. That's a good hypothesis. That's actually not the problem in this case. So the answer is that we actually need to explicitly tell TensorFlow that we want to run these new W1 and new W2 operations. So we've built up this big computational graph data structure in memory. And now when we call run, we only told TensorFlow that we wanted to compute loss. And if you kind of look at the dependencies among these different operations inside the graph, you see that in order to compute loss, we don't actually need to perform this update operation. So TensorFlow is smart, and it only computes the parts of the graph that are necessary for computing the output that you asked it to compute. So that's kind of a nice thing, because it means it's only doing as much work as it needs to. But in situations like this, it can be a little bit confusing and lead to behavior that you didn't expect. So the solution in this case is that we actually need to explicitly tell TensorFlow to perform those update operations. So one thing we could do, which is what was suggested, is we could add new W1 and new W2 as outputs and just tell TensorFlow that we want to produce these values as outputs. But that's a problem too, because the values, those new W1, new W2 values are, again, these big GPUs, or these big tensors. So now if we tell TensorFlow we want those as output, we're going to, again, get this copying behavior between CPU and GPU at every iteration. So that's bad. We don't want that. So there's a little trick you can do instead, which is that we add kind of a dummy node to the graph with these fake data dependencies. And we just say that this dummy node updates has these data dependencies of new W1 and new W2. And now when we actually run the graph, we tell it to compute both the loss and this dummy node. And this dummy node doesn't actually return any value. It just returns none. But because of this dependency that we've put into the node, it ensures that when we run the updates value, we actually also run these update operations. So question? Is there a reason that we didn't put x and y into the graph and that it stayed as NumPy? So in this example, we're reusing x and y, we're reusing the same x and y on every iteration. So you're right, we could have just also stuck those in the graph. But in a more realistic scenario, x and y will be mini batches of data. So those will actually change at every iteration, and we will want to feed different values for those at every iteration. So in this case, they could have stayed in the graph, but in most cases, they will change. So we don't want them to live in the graph. So now this is, another question? So we told it, we put into TensorFlow that the outputs we want are loss and updates. Updates is not actually a real value. So when updates evaluates, it just returns none. But because of this dependency, we've told it that updates depends on these assign operations. But these assign operations live inside the computational graph and all live inside GPU memory. So then we're doing these update operations entirely on the GPU, and we're no longer copying the updated values back out of the graph. So the question is, does tf.group return none? So this gets into the trickiness of TensorFlow. So tf.group returns some crazy TensorFlow value. It doesn't actually, it sort of returns some like internal TensorFlow node operation that we need to continue building the graph. But when you execute the graph and when you tell inside the session.run, when we told it we wanted to compute the concrete value from updates, then that returns none. So whenever you're working with TensorFlow, you have this funny indirection between like building the graph and then the actual output values during building the graph is some funny weird object. And then you actually get a concrete value when you run the graph. So here, after you run updates, then the output is none. Does that clear it up a little bit? Is why is loss a value and why is updates none? That's just the way that updates works. So loss is a value. When we tell TensorFlow we want to run a tensor, then we get the concrete value. Updates is this kind of special other data type that does not return a value. It instead returns none. So it's kind of some TensorFlow magic that's going on there. Maybe we can talk offline if you're still confused. Yeah, so that behavior is coming from the group method. So now we kind of had this weird pattern where we wanted to do these different assign operations. We have to use this funny tf.group thing. That's kind of a pain. So thankfully, TensorFlow gives you some convenience operations that kind of do that kind of stuff for you. And that's called an optimizer. So here, we're using a tf.train.gradient descent optimizer, and we're telling it what learning rate we want to use. And you can imagine that there's Atom, there's RMSProp, there's all kinds of different optimization algorithms here. And now we call optimizer.minimize of loss. And now this is a pretty magical thing, because now this call is aware that these variables W1 and W2 are marked as trainable by default. So then internally inside this optimizer.minimize, it's going in and adding nodes to the graph, which will compute gradient of loss with respect to W1 and W2. And then it's also performing that update operation for you, and it's doing the grouping operation for you, and it's doing the assigns. It's like doing a lot of magical stuff inside there. But then it ends up giving you this magical updates value, which if you dig through the code, they're actually using tf.group. So it looks very similar internally to what we saw before. And now when we run the graph inside our loop, we do the same pattern of telling it to compute loss and updates. And every time we tell the graph to compute updates, then it'll actually go and update the graph. Question? What is the tf.global variables initializer? So that's initializing W1 and W2, because these are variables which live inside the graph. So we need to, when we saw this, when we create the tf.variable, we have this tf.random normal, which is this initialization. So the tf.global variables initializer is causing the tf.random normal to actually run and generate concrete values to initialize those variables. So it knows that a placeholder is going to be fed outside the graph, and a variable is something that lives inside the graph. So I don't know all the details about how it decides, what exactly it decides to run with that call. I think you'd have to dig through the code to figure that out, or maybe it's documented somewhere. But now we've kind of got this again, we've got this full example of training a network in TensorFlow, and we're kind of adding bells and whistles to make it a little bit more convenient. So we can also here, in the previous example, we were computing the loss explicitly using our own tensor operations. TensorFlow, like you can always do that. You can use basic tensor operations to compute just about anything you want. But TensorFlow also gives you a bunch of sort of convenience functions that compute these common neural network things for you. So in this case, we can use tf.losses.mean squared error, and it just does the L2 loss for us, so we don't have to compute it ourselves in terms of basic tensor operations. So another kind of weirdness here is that it was kind of annoying that we had to explicitly define our inputs and define our weights and then like chain them together in the forward pass using a matrix multiply. And in this example, we've actually not put biases in the layer because That would be kind of an extra, then we'd have to initialize biases, we'd have to get them in the right shape, we'd have to broadcast the biases against the output of the matrix multiply, and you could see that that would kind of be a lot of code. It would be kind of annoying to write. And once you get to like convolutions and batch normalizations and other types of layers, this kind of basic way of working of like having these variables, having these inputs and outputs, and combining them all together with basic computational graph operations could be a little bit unwieldy. And it could be really annoying to like make sure you initialize the weights with the right shapes and all that sort of stuff. So as a result, there's a bunch of sort of higher level libraries that wrap around TensorFlow and handle some of these details for you. So one example that ships with TensorFlow is this tf.layers inside. So now in this code example, you can see that our code is only explicitly declaring the x and the y, which are the placeholders for the data and the labels. And now we say that h equals tf.layers.dense. We give it the input x, and we tell it units equals h. And now this will this is, again, kind of a magical line, because inside this line, it's kind of setting up w1 and b1, the bias. It's setting up variables for those with the right shapes that are kind of inside the graph, but a little bit hidden from us. And it's using this Xavier initializer object to set up an initialization strategy for those. So before, we were doing that explicitly ourselves with this tf.randomNormal business. But now here, it's kind of handling some of those details for us. And it's just spitting out an h, which is, again, the same sort of h that we saw in the previous layer. It's just doing some of those details for us. And you can see here, we're also passing an activation equals tf.nn.relu. So it's even doing the activation, the ReLU activation function inside this layer for us. So it's taking care a lot of these architectural details for us. Question? Does the Xavier initializer default to a particular distribution? I'm sure it has some default. I'm not sure what it is. I think you'll have to look at the documentation. But it seems to be a reasonable strategy, I guess. And in fact, if you run this code, it converges much faster than the previous one because the initialization is better. And you can see that we're using 2 calls to tf.layers, and this lets us build our model without doing all these explicit bookkeeping details ourselves. So this is maybe a little bit more convenient. But tf.contrib.layers is really not the only game in town. There's like a lot of different higher level libraries that people build on top of TensorFlow. And it's kind of due to this like basic impedance mismatch, where the computational graph is a relatively low level thing. But when we're working with neural networks, we have this concept of layers and weights, and some layers have weights associated with them, and we typically think at a slightly higher level of abstraction than this raw computational graph. So that's what these various packages are trying to help you out and let you work at this higher layer of abstraction. So another very popular package that you may have seen before is Keras. Keras is a very beautiful, nice API that sits on top of TensorFlow and handles sort of building up these computational graphs for you up in the back end. So by the way, Keras also supports Theano as a backend, so that's also kind of nice. And in this example, you can see we build the model as a sequence of layers. We build some optimizer object, and we call model.compile, and this does a lot of magic in the backend to build the graph. And now we can call model.fit, and that fit does the whole training procedure for us magically. So I don't know all the details of how this works, but I know Keras is very popular, so you might consider using it if you're talking about TensorFlow. Question? Yeah, so the question is like, why? Well, there's no explicit CPU, GPU going on here. So I've kind of left that out to keep the code clean. But you saw at the beginning examples, it was pretty easy to flop all these things between CPU and GPU. And there's either some global flag or some different data type or like some with statement. And it's usually relatively simple and just about one line to swap in each case. But exactly what that line looks like differs a bit exactly depending on the situation. So there's actually like this whole large set of higher level TensorFlow wrappers that you might see out there in the wild. And it seems that like even people within Google can't really agree on which one is the right way to use, but which one is the right one to use. So Keras and TF-Learn are third-party libraries that are out there on the internet by other people. But there's these 3 different ones, tf.layers, tf-slim, and tf.contrib.learn, that all ship with TensorFlow, that are all kind of doing this a slightly different version of this higher level wrapper thing. There's another framework also from Google, but not shipping with TensorFlow, called PrettyTensor, that does the same sort of thing. And And I guess none of these were good enough for DeepMind because they went ahead a couple weeks ago and wrote and released their very own high-level TensorFlow wrapper called Sonnet. So I wouldn't begrudge you if you were kind of confused by all these things. There's a lot of different choices. They don't always play nicely with each other. But you have a lot of options, so that's good. TensorFlow has pre-trained models. There's some examples in TF-Slim and in Keras, because remember, pre-trained models are super important when you're training your own things. There's also this idea of TensorBoard, where you can load up your, I don't want to get into the details, but TensorBoard, you can add sort of instrumentation to your code and then plot losses and things as you go through the training process. TensorFlow also lets you run distributed, where you can break up a computational graph, run on different machines. That's super cool, but I think probably not really anyone outside of Google is really using that to great success these days. But if you do want to run distributed stuff, probably TensorFlow is the main game in town for that. A side note is that a lot of the design of TensorFlow is kind of spiritually inspired by this earlier framework called Theano from Montreal. I don't want to go through the details here. Just if you go through these slides on your own, you can see that the code for Theano ends up looking very similar to TensorFlow, where we define some variables, we do some forward pass, we compute some gradients, and we compile some function. Then we run the function over and over to train the network. So it kind of looks a lot like TensorFlow. So we still have a lot to get through, so I'm going to move on to PyTorch and maybe take questions at the end. PyTorch from Facebook is kind of different from TensorFlow in that we have sort of 3 explicit different layers of abstraction inside PyTorch. So PyTorch has this tensor object, which is just like a NumPy array. It runs imperatively on, it's just an imperative array. It doesn't know anything about deep learning, but it can run on the GPU. We have this variable object, which is a node in a computational graph, which builds up computational graphs, lets you compute gradients, that sort of thing. And we have a module object, which is a neural network layer that you can compose together these modules to build big networks. So if you kind of want to think about rough equivalents between PyTorch and TensorFlow, you can think of the PyTorch tensor as fulfilling the same role as the NumPy array in TensorFlow. The PyTorch variable is similar to the TensorFlow tensor or variable or placeholder, which are all sort of nodes in a computational graph. And now the PyTorch module is kind of equivalent to these higher level things from tf.slim or tf.layers or Sonnet or these other higher level frameworks. So right away, one thing to notice about PyTorch is that because it ships with this higher level abstraction and like one really nice higher level abstraction called modules on its own, there's sort of less choice involved. Just stick with the NN modules and you'll be good to go. You don't need to worry about which higher level wrapper to use. So PyTorch tensors, as I said, are just like NumPy arrays. So here on the right, we've done an entire 2-layer network using entirely PyTorch tensors. One thing to note is that we're not importing NumPy here at all anymore. We're just doing all these operations using PyTorch tensors. And this code looks exactly like sort of the 2-layer net code that you wrote in NumPy on the first homework. So you set up some random data, you use some operations to compute the forward pass, and then we're explicitly doing the backward pass ourselves, just sort of backpropping through the network, through the operations, just as you did on homework 1. And now we're doing a manual update of the weights using our learning rate and using our computed gradients. And it's really, but the major difference between the PyTorch tensor and NumPy arrays is that they run on GPU. So all you have to do to make this code run on GPU is use a different data type. Rather than using torch.floatTensor, you do torch.CUDA.floatTensor. Cast all of your tensors to this new data type, and everything runs magically on the GPU. So you should think of PyTorch tensors as just NumPy plus GPU. That's exactly what it is. Nothing specific to deep learning. So the next layer of abstraction in PyTorch is the variable. So this is, once we move from tensors to variables, now we're building computational graphs, and we're able to take gradients automatically and everything like that. So here, if x is a variable, then x.data is a tensor, and x.grad is another variable containing the gradients of the loss with respect to that tensor. So x.grad.data is an actual tensor containing those gradients. And PyTorch tensors and variables have the exact same API. So any code that worked on PyTorch tensors, you can just make them variables instead and run the same code, except now you're building up a computational graph rather than just doing these imperative operations. So here we've done the exact same. So here, when we create these variables, each call to the variable constructor wraps a PyTorch tensor, and then also gives a flag whether or not we want to compute gradients with respect to this variable. And now in the forward pass, it looks exactly like it did before in the variable in the case with tensors because they have the same API. So now we're computing our predictions, we're computing our loss in kind of this imperative kind of way. And then we call loss.backwards, and now all these gradients come out for us. And then we can make a gradient update step on our weights using the gradients that are now present in the w1.grad.data. So this ends up looking quite like the NumPy case, except all the gradients come for free. One thing to note that's kind of different between PyTorch and TensorFlow is that in the TensorFlow case, we were building up this explicit graph, then running the graph many times. Here in PyTorch, instead, we're building up a new graph every time we do a forward pass. And this makes the code look a bit cleaner. And it has some other implications that we'll get to in a bit. So in PyTorch, you can define your own new autograd functions by defining the forward and backward in terms of tensors. This ends up looking kind of like the module layers code that you write for homework 2, where you can implement forward and backward using tensor operations, and then stick these things inside computational graphs. So here we're defining our own ReLU, and then we can actually go and use our own ReLU operation and now stick it inside our computational graph and define our own operations this way. But most of the time, you will probably not need to define your own autograd operations. Most of the times, the operations you need will mostly be already implemented for you. So in TensorFlow, we saw if we can move to something like Keras or tf.learn, and this gives us a higher level API to work with rather than this raw computational graphs. The equivalent in PyTorch is the NN package, where it provides these high-level wrappers for working with these things. So, but unlike TensorFlow, there's only one of them, and it works pretty well, so just use that if you're using PyTorch. So here, this ends up looking kind of like Keras, where we define our model as some sequence of layers of linear and ReLU operations, and we use some loss function defined in the NN package that's our mean squared error loss. And now inside each iteration of our loop, we can run data forward through the model to get our predictions. We can run the predictions forward through the loss function to get our scalar loss. Then we can call loss.backward, get all our gradients for free, and then loop over the parameters of the models and do our explicit gradient descent step to update the models. And again, we see that we're sort of building up this new computational graph every time we do a forward pass. And just like we saw in TensorFlow, PyTorch provides these optimizer operations that kind of abstract away this updating logic and implement fancier update rules like Atom and whatnot. So here we're constructing an optimizer object, telling it that we want it to optimize over the parameters of the model, giving it some learning rate on other hyperparameters. And now, after we compute our gradients, we can just call optimizer.step, and it updates all the parameters of the model for us right here. So another common thing you'll do in PyTorch a lot is actually define your own NN modules. So typically, you'll write your own class, which defines your entire model as a single new NN module class. And a module is just kind of a neural network layer that can contain either other modules or trainable weights or other kinds of state. So in this case, we can redo the two-layer net example by defining our own NN module class. So now here in the initializer of the class, we're assigning this linear 1 and linear 2. We're constructing these new module objects and then storing them inside of our own class. And now in the forward pass, we can use both our own internal modules as well as arbitrary autograd operations on variables to compute the output of our network. So here we receive the inside this forward method here, the input x is a variable. And then we pass the variable to our self.linear1 for the first layer. We use an autograd op clamp to compute the ReLU. We pass the output of that to the second linear, and then that gives us our output. And now the rest of this code for training this thing looks pretty much the same, where we build an optimizer, a loop over, and on every iteration, feed data to the model, compute the gradients with loss.backwards, call optimizer.step. So this is like relatively characteristic of what you might see in a lot of PyTorch type training scenarios, where you define your own class, defining your model that contains other modules and whatnot, and then you have some explicit training loop like this that runs it and updates it. One kind of nice quality of life thing that you have in PyTorch is a data loader. So a data loader can handle building mini batches for you. It can handle some of the multi-threading that we talked about for you, where it can actually use multiple threads in the background to build mini batches for you and stream off disk. So here, a data loader wraps a data set and provides some of these abstractions for you. And in practice, when you want to run your own data, you typically will write your own data set class, which knows how to read your particular type of data off whatever source you want, and then wrap it in a data loader and train with that. So here we can see that now we're iterating over the data loader object. And at every iteration, this is yielding mini batches of data. And it's internally handling the shuffling of the data and multi-threaded data loading and all this sort of stuff for you. So this is kind of a complete PyTorch example. And a lot of PyTorch training code ends up looking something like this. PyTorch provides pre-trained models. And this is probably the slickest pre-trained model experience I've ever seen. You just say torchvision.models.alexnet pre-trained equals true. And that'll go down in the background, download the pre-trained weights for you if you don't already have them. And then it's right there. You're good to go. So this is super easy to use. PyTorch also there's also a package called Visdom that lets you visualize some of these loss statistics, somewhat similar to TensorBoard. So that's kind of nice. I haven't actually gotten a chance to play around with this myself, so I can't really speak to how useful it is. But one of the major differences between TensorBoard and Visdom is that TensorBoard actually lets you visualize the structure of the computational graph, which is really cool, a really useful debugging strategy. And Visdom does not have that functionality yet. But I've never really used this myself, so I can't really speak to its utility. As a bit of an aside, PyTorch is kind of an evolution of kind of a newer, updated version of an older framework called Torch, which I worked with a lot in the last couple of years. And I don't want to go through the details here, but PyTorch is pretty much better in a lot of ways than the old Lua Torch. But they actually share a lot of the same backend C code for computing with tensors and GPU operations on tensors and whatnot. So if you look through this Torch example, some of it ends up looking kind of similar to PyTorch. Some of it's a bit different. Maybe you can step through this offline. But kind of the high-level differences between Torch and PyTorch are that Torch is actually in Lua, not Python, unlike these other things. So learning Lua is a bit of a turnoff for some people. Torch doesn't have autograd. Torch is also older, so it's more stable, less susceptible to bugs. There's maybe more example code for Torch. They're about the same speeds. That's not really a concern. But in PyTorch, it's in Python, which is great. You've got autograd, which makes it a lot simpler to write complex models. In LuaTorch, you end up writing a lot of your own backprop code sometimes, so that's a little bit annoying. But PyTorch is newer. There's less existing code. It's still subject to change. So it's a little bit more of an adventure. But at least for me, I kind of prefer I don't really see much reason for myself to use Torch over PyTorch anymore at this time. So I'm pretty much using PyTorch exclusively for all my work these days. We talked about this a little bit, about this idea of static versus dynamic graphs. And this is one of the main distinguishing features between PyTorch and TensorFlow. So we saw in TensorFlow, you have these two stages of operation, where first you build up this computational graph, then you run the computational graph over and over again many, many times, reusing that same graph. So that's called a static computational graph, because there's only one of them. And we saw PyTorch was quite different, where we're actually building up this new computational graph, this new fresh thing on every forward pass. So that's called a dynamic computational graph. For kind of simple cases with kind of feed-forward neural networks, it doesn't really make a huge difference. The code ends up looking kind of similarly, and they work kind of similarly. But I do want to talk a bit about some of the implications of static versus dynamic, and what are the trade-offs of those two. So one kind of nice idea with static graphs is that because we're kind of building up one computational graph once, and then reusing it many times, the framework might have the opportunity to go in and do optimizations on that graph and kind of fuse some operations, reorder some operations, figure out the most efficient way to operate that graph so it can be really efficient. And because we're going to reuse that graph many times, maybe that optimization process is expensive up front, but we can amortize that cost with the speedups that we've gotten when we run the graph many, many times. So as kind of a concrete example, maybe if you write some graph which has convolution and ReLU operations kind of one after another, you might imagine that some fancy graph optimizer could go in and actually emit custom code which has fused operations fusing the convolution and the ReLU. So now it's computing the same thing that you did as the code you wrote, but now might be able to be executed much more efficiently. So I'm not too sure on exactly what the state in practice of TensorFlow graph optimizations is right now, but at least in principle, this is one place where a static graph really, you can do this, you can have the potential for doing this optimization in static graphs where it maybe would be not so tractable for dynamic graphs. Another kind of subtle point about static versus dynamic is this idea of serialization. So with a static graph, you can imagine that you write this code that builds up the graph, and then once you've built the graph, you have this data structure in memory that represents the entire structure of your network. And now you could take that data structure and just serialize it to disk. And now you've got the whole structure of your network saved in some file, and then you could later reload that thing and then run that computational graph without access to the original code that built it. So this would be kind of nice in a deployment scenario. You might imagine that you might want to train your network in Python because it's maybe easier to work with. But then after you serialize that network, and then you could deploy it now in maybe a C++ environment where you don't need to use the original code that built the graph. So that's kind of a nice advantage of static graphs. Whereas with a dynamic graph, because we're interleaving these processes of graph building and graph execution, you kind of need the original code at all times if you want to reuse that model in the future. On the other hand, some advantages for dynamic graphs are that it just makes your code a lot cleaner and a lot easier in a lot of scenarios. So for example, suppose that we wanted to do some conditional operation where depending on the value of some variable z, we want to do different operations to compute y. Where if z is positive, we want to use one weight matrix. If z is negative, we want to use a different weight matrix. And we just want to switch off between these two alternatives. In PyTorch, because we're using dynamic graphs, it's super simple. Your code kind of looks exactly like you would expect, like exactly what you would do in NumPy. You can just use kind of normal Python control flow to handle this thing. And now, because we're building up the graph each time we perform this operation, we'll take one of the two paths and build up maybe a different graph on each forward pass. But for any graph that we do end up building up, we can backpropagate through it just fine. And the code is very clean, easy to work with. Now in TensorFlow, the situation is a little bit more complicated. Because we build the graph once, this control flow operator kind of needs to be an explicit operator in the TensorFlow graph. And now, so then you can see that we have this tf.cond call, which is kind of like a TensorFlow version of an if statement, but now it's baked into the computational graph rather than using sort of Python control flow. And the problem is that because we only build the graph once, all the potential paths of control flow that our program might flow through need to be baked into the graph at the time we construct it, before we ever run it. So that means that any kind of control flow operators that you want to have need to be not Python control flow operators. You need to use some kind of magic special TensorFlow operations to do control flow. In this case, is tf.cond. Another kind of similar situation happens if you want to have loops. So suppose that we want to compute some kind of recurrent relationship where maybe yt is equal to yt minus 1 plus xt times some weight matrix w. And then depending on each time we do this, every time we compute this, we might have a different sized sequence of data. And no matter the length of our sequence of data, we just want to compute this same recurrence relation no matter the size of the input sequence. So in PyTorch, this is super easy. We can just kind of use a normal for loop in Python to just loop over the number of times that we want to unroll. And now, depending on the size of the input data, our computational graph will end up as different sizes. But that's fine. We can just backpropagate through each one at a time. Now, in TensorFlow, this becomes a little bit uglier. And again, because we need to construct the graph all at once up front, this control flow looping construct, again, needs to be an explicit node in the TensorFlow graph. So I hope you remember your functional programming, because you'll have to use those kinds of operators to implement looping constructs in TensorFlow. So in this case, for this particular recurrence relationship, you can use a fold-L operation and sort of implement this particular loop in terms of a fold-L. But what this basically means is that you have this sense that TensorFlow is almost building its own entire programming language in using the language of computational graphs. And any kind of control flow operator, any kind of data structure needs to be rolled into the computational graph. So you can't really utilize all your favorite paradigms for working imperatively in Python. You kind of need to relearn a whole separate set of control flow operators, and if you want to do any kinds of control flow inside your computational graphs using TensorFlow. So at least for me, I find that kind of confusing, a little bit hard to wrap my head around sometimes. And I kind of like that using PyTorch dynamic graphs, you can just use your favorite imperative programming constructs, and it all works just fine. By the way, there actually is some very new library called TensorFlow Fold, which is kind of a layer, another one of these layers on top of TensorFlow that lets you implement dynamic graphs. You kind of write your own code using TensorFlow Fold that looks kind of like a dynamic graph operation. And then TensorFlow Fold does some magic for you and somehow implements that in terms of these static TensorFlow graphs. This is a super new paper that's being presented at ICLR this week in France. So I haven't had the chance to like dive in and play with this yet. But my initial impression was that it does add some amount of dynamic graphs to TensorFlow, but it is still a bit more awkward to work with than the sort of native dynamic graphs you have in PyTorch. So then I thought it might be nice to motivate, like, why would we care about dynamic graphs in general? So one option is recurrent networks. So you can see that for something like image captioning, we use a recurrent network which operates over sequences of different lengths. In this case, the sentence that we want to generate as a caption is a sequence, and that sequence can vary depending on our input data. So now you can see that we have this dynamism in the thing, where depending on the size of the sentence, our computational graph might need to have more or fewer elements. So that's one kind of common application of dynamic graphs. For those of you who took CS224N last quarter, you saw this idea of recursive networks, where sometimes in natural language processing, you might, for example, compute a parse tree of a sentence, and then you want to have a neural network kind of operate recursively up this parse tree. So having a neural network that kind of works it's not just a sequential sequence of layers, but instead it's kind of working over some graph or tree structure instead, where now each data point might have a different graph or tree structure. So the structure of the computational graph then kind of mirrors the structure of the input data, and it could vary from data point to data point. So this type of thing seems kind of complicated and hairy to implement using TensorFlow. But in PyTorch, you can just kind of use like normal Python control flow, and it'll work out just fine. Another bit of more researchy application is this really cool idea that I like called neural module networks for visual question answering. So here, the idea is that we want to ask some questions about images, where we maybe input this image of cats and dogs. There's some question, what color is the cat? And then internally, the system can read the question and then has these different specialized neural network modules for performing operations like asking for colors and finding cats. And then depending on the text of the question, it can compile this custom architecture for answering the question. And now if we asked a different question, like, are there more cats than dogs? Now we have maybe the same basic set of modules for doing things like finding cats and dogs and counting, but they're arranged in a different order. So we get this dynamism, again, where different data points might give rise to different computational graphs. But this is a bit more of a researchy thing and maybe not so mainstream right now. But as kind of a bigger point, I think that there's a lot of cool creative applications that people could do with dynamic computational graphs. And maybe there aren't so many right now just because it's been so painful to work with them. So I think that there's a lot of opportunity for doing cool, creative things with dynamic computational graphs. And maybe if you come up with cool ideas, we'll feature it in lecture next year. So I wanted to talk very briefly about Caffe, which is this framework from Berkeley, which Caffe is somewhat different from the other deep learning frameworks, where in many cases, you can actually train networks without writing any code yourself. You kind of just call into these pre-existing binaries, set up some configuration files, and in many cases, you can train on data without writing any of your own code. So first you convert your data into some format like HDF5 or LMDB, and there exists some scripts inside Caffe that can just convert like folders of images and text files into these formats for you. You need to define, now instead of writing code to define the structure of your computational graph, instead you edit some text file called a proto.txt, which sets up the structure of the computational graph. Here, the structure is that we read from some input HDF5 file, we perform some inner product, we compute some loss, and the whole structure of the graph is set up in this text file. One kind of downside here is that these files can get really ugly for very large networks. So for something like the 152-layer ResNet model, which, by the way, was trained in Caffe originally, then this proto.txt file ends up almost 7,000 lines long. So people are not writing these by hand. People sometimes will like write Python scripts to generate these proto.txt files, and then you're kind of in the realm of rolling your own computational graph abstraction. That's probably not a good idea, but I've seen that before. Then rather than having some optimizer object, instead there's some solver. You define some solver things inside another proto.txt. This defines your learning rate, your optimization algorithm, and whatnot. And then once you do all these things, you can just run the Caffe binary with the train command, and it all happens magically. Caffe has a model zoo with a bunch of pre-trained models. That's pretty useful. Caffe has a Python interface, but it's not super well documented. You kind of need to read the source code of the Python interface to see what it can do. So that's kind of annoying, but it does work. So kind of my general output, my general thing about Caffe is that it's maybe good for feed-forward models. It's maybe good for production scenarios because it doesn't depend on Python. But probably for research these days, I've seen Caffe being used maybe a little bit less. Although I think it is still pretty commonly used in industry, again, for production. I promise one or two slides on Caffe 2. So Caffe 2 is this successor to Caffe, which is from Facebook. It's super new. It was only released a week ago. So I really haven't had the time to form a super educated opinion about Caffe 2 yet. But it uses static graphs, kind of similar to TensorFlow. Kind of like Caffe 1, the core is written in C++, and they have some Python interface. The difference is that now you no longer need to write your own Python scripts to generate proto.txt files. You can kind of define your computational graph structure all in Python, kind of looking with an API that looks kind of like TensorFlow. But then you can spit out, you can serialize this computational graph structure to a proto.txt file. And then once your model is trained and whatnot, then we get this benefit that we talked about of static graphs, where you don't need the original training code now in order to deploy a trained model. So one interesting thing is that we've seen Google maybe has one major deep learning framework, which is TensorFlow, where Facebook has these two, both PyTorch and Caffe 2. So these are kind of different philosophies. Google's kind of trying to build one framework to rule them all that maybe works for every possible scenario for deep learning. This is kind of nice because it's consolidates all efforts onto one framework. It means you only need to learn one thing, and it'll work across many different scenarios, including distributed systems, production, deployment, mobile, research, everything. Only need to learn one framework to do all these things. Whereas Facebook is taking a bit of a different approach, where PyTorch is really more specialized, more geared towards research. So in terms of writing research code and quickly iterating on your ideas, that's super easy in PyTorch. But for things like running in production, running on mobile devices, PyTorch doesn't have a lot of great support. Instead, Caffe 2 is kind of geared towards those more production-oriented use cases. So my kind of general study, my general overall advice about which framework to use for which problems is kind of that I think TensorFlow is a pretty safe bet for just about any project that you want to start new, right? Because it is sort of one framework to rule them all. It can be used for just about any circumstance. However, you probably need to pair it with a higher level wrapper. And if you want dynamic graphs, you're maybe out of luck. Some of the code ends up looking a little bit uglier in my opinion, but maybe that's kind of a cosmetic detail and it doesn't really matter that much. I personally think PyTorch is really great for research. If you're focused on just writing research code, I think PyTorch is a great choice. But it's a bit newer, it has less community support, less code out there, so it could be a bit of an adventure. If you want more of a well-trodden path, TensorFlow might be a better choice. If you're interested in production deployment, you should probably look at Caffe, Caffe 2, or TensorFlow. And if you're really focused on mobile deployment, I think TensorFlow and Caffe 2 both have some built-in support for that. So it's kind of unfortunate. There's not just one global best framework. It kind of depends on what you're actually trying to do, what applications you anticipate. But these are kind of my general advice on those things. So next time, we'll talk about some case studies about various CNN architectures.